Hello everyone and welcome back to the class. Now in the analysis of first order circuits, we will study the step response of an RC circuit. As discussed earlier, we know that the first order circuits can be excited by two methods. First method is to use the initial condition of storage element, and it is assumed that the storage element was initially charged, and these circuits are known as source-free circuits. Where second method is to excite the first order circuit with the help of independent sources. And now we will study the second method, in which we will excite the given circuits with the help of independent DC sources. And we will begin this by a step response. Whenever a DC source is suddenly applied to an RC or RL circuit, the voltage or current can be modeled as a step function, and the response of the circuit will be known as the step response. Or alternatively, the step response is the response of the circuit due to sudden application of the DC voltage or the DC current. Now formally, the step response of a circuit will be defined as the step response of a circuit is its behavior when the excitation is a step function, which may be a current or a voltage source. Now we have a mathematical and graphical representation of a step function. If you look at figure 1, which represents a unit step function, the step function u of t is plotted against time t. For time less than 0 or for negative value of time, the function u of t have a value of 0, and for time t greater than 0 or for positive value of time, the function have value of 1. And at time t equals to 0, this transition from 0 to 1 occurs. So it is undefined for time t equals to 0. And this is also dimensionless like other mathematical functions such as cos or sine. Now if the abrupt change in the value of function u of t occurs at time t equals to t naught instead of time t equal to 0, and t naught is a positive number, then mathematically the step function will be represented as u of t minus t naught, and it will be 0 for time t less than t naught, and it will have value of 1 for time t greater than t naught. And this step function u of t minus t naught is graphically represented in figure 2a, which shows that the step function is delayed by a t naught seconds. Now if the abrupt change in the value of step function occurs at time t equals to minus t naught, then the step function will be represented as u of t plus t naught, and this function will have value of 0 for time t less than minus t naught and a value of 1 for time t greater than minus t naught, and is graphically represented in figure 2b. This graph also shows that the change in step function or in output is advanced by a t naught seconds. Now after the overview of step function, we will study the step response of an RC circuit. For this analysis, consider the circuit in figure 3. The RC circuit in figure 3 has source voltage of V of S, and the capacitor have a voltage of V. The voltage V will be the response of the circuit, which we will determine. And for this we will make assumption that initial voltage stored across capacitor will be V naught. And the voltage across capacitor cannot change instantaneously, so the voltage across capacitor at the instant before and after the applying of source voltage will be same and is represented by V naught. Here V of 0 negative is the voltage across capacitor before switching, and V of 0 positive is the voltage across capacitor after the switching. Now for analysis purpose, we will apply KCL and will assume that current leaving from resistor is equal to the current entering to the capacitor. Now the current entering in the capacitor will be C dV by dt, and current leaving from the resistor will be Vsu of t minus node voltage V divided by R. Now rearranging the variables, we will have dV over dt plus V over RC will be equal to Vsu of t over RC. Doing analysis when step voltage is applied, and this step voltage will be applicable for time t greater than 0. So the last equation will be turned into dv over dt plus v over rc equals vs over rc. Now rearranging this equation, we will reach to the result dv over v minus vs equals minus dt over rc. Now for the response of the circuit, which is capacitor voltage V, we will integrate both sides of the equation, which will give us natural log of V minus Vs with integration limit starting from V0 to V of t will be equal to minus t over Rc, and this term will have limit of from time t equals to 0 to present time t. Now substituting the integral limits and using logarithmic properties, we will have natural log of v minus vs divided by v0 minus vs will be equal to minus t over. Now to find function v of t, take exponential of both sides. Now solving this, we will reach to the result that v of t is equal to vs plus v0 minus vs multiplied by exponential of minus t over tau, where tau is equal to Rc, which is the time constant of RC circuit. And this equation of v of t represent circuit response for time t greater than 0. And for time t less than 0, we know that the voltage across capacitor was V0. So the voltage v of t in terms of piecewise function will be, for time t less than 0, v of t will have value of v0. For time t greater than 0, v of t will have value of vs plus v0 minus vs whole multiplied by exponential power minus t over tau. And this function represents the total response of an RC circuit when capacitor was initially charged. If applied source voltage Vs is greater than initial voltage of capacitor V0, then total response is represented in figure 4. Now if we assume that the capacitor was initially uncharged, then initial voltage of capacitor V0 will be equal to 0. So in this case, the total response V of t will be expressed as, when time t is less than 0, the voltage across capacitor will be of 0 volts, and when time t is greater than 0, the total voltage will be equal to 1 minus exponential of minus t over tau. And this can also be expressed as V of t equals Vs into 1 minus exponential of minus t over tau u of t. And this is the complete response of RC circuit when the capacitor was initially uncharged. Now we will make analysis for current passing through the capacitor, and current is equal to the capacitance of capacitor multiplied by rate of change of voltage across the capacitor, and substituting the value of voltage for time t greater than 0, I of t will be equal to capacitance of capacitor divided by time constant tau product with source voltage Vs product with exponential of minus t over tau, where tau is the time constant and is equal to Rc. Now the current through resistor will be source voltage divided by resistance of resistor in product with exponential power minus t over tau u of t. Now the figure 5 represents step response of RC circuit, and the capacitor of this RC circuit was initially uncharged. Figure A represents voltage response, which starts from 0 and gradually rises to the value of Vs. For current at time t equals to 0 have value of Vs over R, and this current gradually decays to 0. In this example, for the circuit in figure 6, a switch was closed for a long time and is opened at time t equals to 0. You have to find current and voltage response for all values of time. The circuit consists of a 30 volts step voltage source, 2 resistors and 1 capacitor, and 1 independent DC voltage source. Now we will start the solution. The current through resistor can be discontinuous at time t equals to 0, where the capacitor voltage cannot be. So it is always better to find voltage V, and then with the help of Ohm's law we can find the current. And by definition of step function, we know that 30 u of t will be equal to 0 when time t is less than 0 and will have value of 30 for time t greater or equal to 0. Now for this circuit, we will make analysis in two parts. First of all, we will make analysis for time t less than 0 and then we will make analysis for time t greater than 0. Now starting with time t less than 0, we know that the 30 u of t will equal to 0, so the voltage source will be replaced by a short circuit. And this source will contribute no voltage. And the resultant circuit is shown in the figure 7. As per statement of the example, the switch was closed for a long time, so the capacitor is initially charged and will act as an open circuit for DC independent source. Now from figure 7, the voltage V will be equal to 10 volts and the current I passing through 10 ohm resistor will be equal to negative of voltage V divided by 10 and will have value of minus 1 amperes. The components in the figure 7 are two resistors and one independent DC voltage source, and all these components are in parallel. And in actual, the current is moving from 10 voltage source to these resistors. But current I is opposite to the actual current, so that's why there is a negative sign in the value of current I. And we know that voltage across capacitor cannot change instantaneously, so the voltage before and after switching will be the same and will have value of 10 volts. Now for time t greater than 0, the switch will be open and the 10 volt independent voltage source will be disconnected from the circuit, and the 30 volt step voltage source will be operative, and the resultant circuit is shown in the figure 8. Here again, after charging, the capacitor will act as an open circuit due to DC source. Now to find voltage across capacitor, the 20 ohm resistor and 0.25 farad capacitor both are in parallel, so using the voltage division rule, the voltage across capacitor will be equal to of 20 volts. And the given circuit have two resistors, and for analysis purpose, we will transform this into equivalent Thevenin circuit. So our Thevenin will be equal to 10 ohm parallel with 20 ohm and will have value of 20 over 3 ohms. And the time constant will be equal to R Thevenin product with capacitance of capacitor and will have value of 5 over 3 seconds. Now with the help of complete response relation for a RC circuit, which is V of t is equal to Vs plus V0 minus Vs whole multiplied by exponential power minus t over tau. Now substituting the values in the total response relation, the V of t will be equal to 20 minus 10 into exponential power minus 3t over 5 volts. Now we will find current when time t is greater than 0. If you look at figure 8, we know that the current I is the sum of current through resistor and capacitor, so I will be equal to sum of IR plus IC, where the current through resistor will be voltage across resistor divided by resistance of resistor, as both resistor and capacitor are in parallel, so IR will be equal to V divided by 20, and current through capacitor will be product of capacitance of capacitor with rate of change of voltage. Now substituting the values and solving, the current I will be equal to 1 plus exponential power minus 0.6 t amperes. Now we will summarize the all values of voltages and currents. The voltage V will be equal to 10 volt for time less than 0, and for time greater than equal to 0 it will be 20 minus 10 into exponential power minus 0.6 t volts. And current I for time less than 0 will be of minus 1 ampere, and for time t greater than 0 it will be of 1 plus exponential power minus 0.6 t amperes. And thanks for watching this video.